Okay. Nice option. All right. Thank you, everyone, for joining us here across the street, a slightly different place. So today we're very pleased to have Professor Florian Laggner visiting us from North Carolina State. Professor Laggner is a long-time product of Vienna, okay, from the Technical University there. He did his undergraduate and graduate studies there before going to what is without any doubt the best state in the Union act in California, New Jersey. That's where I'm from. Okay, the Garden State, thank you. The Garden State. Yeah, we're not really okay. But before going to New Jersey and doing most of his work at Princeton Plasma Physics Laboratories at that other university. What's it called? I can't remember. Oh, Princeton, that's right. But not at Rutgers. And before making the migration down to North Carolina, where he holds his current position. So today he's going to tell us about towards fusion energy, key physics challenges, and potential engineering solutions.
Thank you for the nice introduction. Welcome also from my side. Thanks for giving me the opportunity to meet some new people, see some new faces, and share a little bit about my research. So, without further ado, there was an introduction. There is also a second one that I've prepared, if I can make it to the extended screen. Let's try to do it like this. Nope. Ha!
There we go.
Okay. Who am I? I'm a fusion enthusiast, but my background is pretty versatile. So up to my master's project, I've been competing in European team handball. And my height definitely helps with that. But what I learned there was already, you have to take a lot of hits in life in order to make it to the goal. But if you make it to the goal, so you win championship trophies, it's even more rewarding for all the pain that you have been putting in to this. And so eventually I thought it's not that healthy to do handball for the rest of my life. I would be retired by now, by the way. And it's not on a salary where I would have been retired like for retirement. So I decided to do my PhD at the Vienna University of Technology, formerly known, now just TU Wien, that's the new brand. So eventually graduated there and then moved on to become Llama team member, and you will learn about the Llama today. And yeah, well, I like to hang out in fusion reactors. So this is a token map from the inside. I've done a lot of installations there, and on the left and bottom, I bring my students into these machines and show them how a fusion experiment actually looks like. One key message on this slide is you typically never see me alone with these pictures, and even if there are my opponents, I still feel that like working together as a team, I value the interaction of other persons, the exchange of different ideas, and I think that has been a key cornerstone of my path in fusion energy engineering. Just to show them pictures of beautiful cities. I think this is the first department where I don't need to explain where Austria is, right? Right? So it's this beautiful place in Central Europe where I spent most of my PhD in this building here, right next to the famous Karlskirche. So if you ever go there, TU Wien has a really good location. But I learned very quickly that what I want to do, which is fusion energy research, is not that big in Austria. So I had to do my PhD in collaboration with the Max Planck Institute for Plasma Physics. So I started to go abroad in Europe, which means to drive 2 hours to get somewhere. So I went to Munich and got my PhD on Aztec's upgrade. And eventually the opportunity came out to jump across the Atlantic and end up at Princeton University to do my postdoc there. And since I didn't do that terrible, and I met a lot of supportive people, and I brought in some good ideas, I was hired as a staff researcher at Princeton Plasma Physics Lab, with the bonus that they say, like, we don't want to have you here, we want to have you out in San Diego. So I did the move coast to coast, came to nice Southern California, and I started doing experiments on D3D and getting heavily involved with the D3D National Fusion Facility. And I'm going to present a little bit about that research today as well. So you work at the national lab, at the big user facility. You have everything. You have resources, you can do fusion. What is missing? Students, okay? You. This is the reason why I pursued the path and pivot and say, like, I cannot do all this work on my own. I need to have interested young minds that come in with fresh energy to pursue these ideas, to guide them and walk them along, and hopefully eventually contributing to this quest of fusion energy. And so I hopped back 2 cross-country moves within 5 years to North Carolina State University, where I'm now developing my lab. And this is going to fall short a little bit in the talk, so I have one slide up front, is my approach to plasma physics in general and fusion energy research is always you need to design and advance new diagnostic tools to get to new insights. If you have a new measurement, if you validate a new measurement, you can study a new physics effect, because sometimes you're just limited within the present technology. So I have like hands-on work on 3 plasma diagnostics: lithium beam, Thomson scattering, and the so-called llama. And these have been kind of the cornerstones to show to achieve most of the physics results that I'm going to show through the rest of the talk. And this also puts a nice segue into what my research is doing. So this is the fusion pack, and this data is the wolf pack. So I had to be very creative to come up with the fusion pack or the F-pack lab. And I'm been working really on a lot of different directions, and I've hired a bunch of grad students to help me with that, because otherwise I'm spread really, really thin. So one of the research areas is tokamak edge physics research. So this is plasma physics, high temperature plasma physics. We're going to talk about this later. Helping to develop plasma diagnostics. So the llama collaboration with MIT, PPPL, and now the new alpaca, which is shown on top, are kind of my babies. We started on a piece of paper, eventually created a logo, and this is now a brand. So if you go and seek somebody from DSUD, you can mention the llama, they will know what this is. And I think this is a really nice project where you start from an idea on paper, and now it has been 5 years down the line. This is data that everybody wants to have in their experiments. I'm working on impurity powder dropping, which is creating really nice images of ablating boron powder in a fusion plasma. So the deuterium, the alpha line, is the pinkish stuff, and then the boron that gets ablated in the tokamak is this nice blue star shower. And then most recently, I started working on neutral beam ion sources. And so for the rest of the, I don't know how many minutes I have, because we started a little bit late, but I would, yeah, for the next 40 minutes, I'm going to like blast through various results. And I think the way I want to connect this is I want to bring up a physics challenge, so a really like a challenge that we are facing in the fusion system, and then provide an engineering solution that I'm like working on to mitigate this kind of Mother Nature not working in the direction you want it to work. And typically it has to do with either controls or it's sort of an actuator that you put in. And so there will be 3 blocks of accomplishments that I'm going to share. Should we ask questions throughout the talk? How do you do this usually?
Yeah, that's fine. Yeah.
I mean, I have no preferences, but I think it's a good break point to start with questions.
Don't be shy.
Don't be shy. No questions yet. Why are there 3? What are the animals on the logo? Very commonly asked question. I can explain that later.
Why llama?
Why llama? Because we are measuring Lyman alpha. And I will have 3 slides on the llama. So we will get the full llama indoctrination and how awesome that is. Why am I talking about high temperature plasma physics? Who knows fusion? Come on now, all hands up. The fundamental source of energy for the universe, you better know that. The challenge is to make it happen. And the Coulomb barrier is really not working in our favor. So positive charges tend to push against each other. And in order to overcome this Coulomb barrier, you need very, very high temperatures on the order of 100 million degrees or kilo electron volts. Kilo electron volt, everybody familiar with a kilo electron volt? Okay, good. the gist of it is that the ionization energy of matter is electron volts. So you require temperatures that are higher than the ionization energy of matter, which means you're naturally going to end up in the state that I've studied for the past 8 years, which are plasmas, okay? And it's not something to be afraid of. It's actually something really, really cool. And it's the form of matter that 99% of our universe, or 99.9% of the universe is. And I just throw up plasmas. You have them in this room, if they are not LEDs up there, but typically you have them very close by in light bulbs. You have them in astrophysical plasmas, and you have them in fusion. And the interesting part, typically you put it on somebody of this chart. You would say magnetic confinement fusion, you need to make these 13 kilo electron volt plasmas to fuse particles. That's true. But in fact, as you move to the wall, which has, let's say, elevated temperature, even if you operate at 1000 Kelvin, that's nothing in comparison to the plasma temperature. So your plasma temperature is actually going to drop down, and the density of the plasma is going to increase. And so there's actually a whole zoo of plasma phenomena that you can study, or regimes that you can study, and this is like at least 2 orders of magnitude in density. A very brief introduction. So you want to keep something very, very hot. You put it in a thermal bottle, right? Doesn't work with fusion plasma so well because they're really tending to cool off quickly if they start to collide with material. And one neat little thing that I'm going to talk about is, well, we can confine it with magnetic fields because we are fully ionized, we have charges. Lorentz force is in our favor. Let's use magnetic field lines to confine a plasma. The easiest way, the Russian figured that out, is to build a toroidal setup, so-called tokamak. And actually these magnetic field coils create a toroidal magnetic field, so the green field. That is not enough to confine the plasma. You need to run a super strong current on the order of mega amps through that plasma. This is the red current that then create a so-called colloidal magnetic field, which are these green arrows going on and around. And what you end up is this yellow helical field line. So you have to have the particles going from the outside of the torus to the inside and to the outside again. That actually creates particle confinement. And tokamak has been very successful because the magnetohydrodynamic equilibrium of such a tokamak basically ensures that your magnetic field lines are on so-called nested flux surfaces, which I illustrated here in the bottom, which means that you have an onion shell-like structure that isolates the plasma between the different layers. And some terms to keep in mind is toroidal, so direction around the torus, and colloidal. And what you also know, if you're batching coils together in like cake piece shapes, the field on the inside is going to be stronger than the outside. So there's a gradient of magnetic field in the radial direction in these tokamaks. And what I've done in the first 5 years of my career is heavily study instabilities in the fusion plasma in the so-called pedestal region.
Since you invited questions.
Yes.
And it shows my ignorance of plasma. I was unaware that the plasma laminates into discrete surfaces.
Yes.
Why is that, and what is the physical condition that leads to that?
So the physical condition is the magnetohydrodynamic stability criterion. It's red P, so the pressure gradient equals to the current flowing in the plasma across P. Yeah. And if you rewrite that in toroidal coordinates with a homogeneous current profile, you basically integrate your current from the center to the edge, and so you ensure that the pitch of these magnetic field lines, so the strength of the magnetic field is always the integral current inside one of these surfaces. Yeah. And so by that theorem, you basically ensure that as soon as you move radially outward, your pitch gets higher and kind of create these nested fluxes.
So you did, the cartoon made it look like there were discontinuities. There's no discontinuity.
There is no discontinuity, no. Right. So they're continuous around the torus. Yeah. Axis symmetry is something very, very nice in plasma physics. So you kind of, rather than going around the torus, you slice a piece out and the plasma is going, like in every toroidal segment, going to look like the same cross section here. And even more important, the particles are trapped to the magnetic field lines. So they are gonna go around the torus on this flux surface, which means that the pressure on one of these surfaces is conserved as well, because of the pressure gradient has to be equal to the current and the magnetic across the magnetic field. And so you can even reduce the dimension there and draw this one-dimensional profile. So this profile over the radius, which is the normalized plasma radius, basically describes the pressure in any direction perpendicular to these flux lines. So that's the reason why you deal a lot with like profiles instead of three-dimensional temperature and pressure maps. And in fusion and tokamak plasmas in the 1980s, a so-called confinement transition has been observed. So this is self-organization by nature. It's actually something really, really cool that you, in the outermost 7%, like this much of your fusion plasma, your fusion reactor has this size, this much, you get a transition where in this low confinement, your pressure gradient is rather flat. You get a steepening of the pressure gradient by a bit, about an order of magnitude in pressure, at least sometimes 2 orders of magnitude. So you have a very, very steep pressure increase, and that basically transits the whole core or center of the plasma pressure also up higher. And that's the reason why it's called pedestal. So it really lifts up that core. And if you integrate basically that pressure, that gives you the stored energy and the fusion power. So the so-called high confinement mode or H mode, the foreseen operation scenario for tokamak fusion reactors, have superb confinement properties in comparison to the low confinement mode. And the H mode discovery is also why tokamaks are basically ahead in fusion energy research in comparison to stellarators or other confinement, magnetic confinement concepts. So now you have a steep pressure gradient, fluid simulations, wherever you have pressure gradients, you have a source of free energy. And so this steep pressure gradient can lead to the instability onset and the collapse of the pedestal, which is the so-called edge localized mode. And my research has been mainly focusing on these edge localized modes because they're very, very severe. So you see the countdown in milliseconds running down. This is a view into a fusion vessel. You see the outer wall. And once you kind of reach 0, you see this big flash of light. That is an edge localized mode instability, throwing out particles and heat to the first wall. In present devices, we can study them because the present devices don't have that much stored power. In real fusion reactors, these edge localized modes are going to melt them all away. So non-tolerable. So this is a physics challenge, right? And what I've studied is basically how these edge localized modes behave, how does this pressure gradient work. So just having that said, so this is the power flux to the wall, and whenever you have this burst, you get a power flux to the wall. So the goal here is to understand edge localized modes, and then ultimately the goal is like how to avoid them. So the engineering solution here is pretty much control. There's also a nice theory that I'll just briefly skim over in the interest of time. So the two sources of energy in this pedestal are the pressure gradient and the current, and that gives a so-called stability boundary where you have stable operation versus an edge localized mode instability. And there are so-called peeling modes, which are kind of onion shell-like modes that have a high field side and a low field side response. And then there are ballooning modes, which are kind of tube pressure modes that dominantly occur at the outward high field side. And whenever you hit this boundary, you will get an elm. This is very well known. But in order to achieve like highest pressure, you actually want to hit the boundary somewhere up here. And the question of my research was, is there some way to avoid this hard limit? So are there any benign instabilities that reduce transport across the edge or increase transport across the edge to avoid this elm limit? And so I've spent a lot of time in studying like high resolution diagnostics, temperature of ions, electrons, rotation of the plasma, electric fields that are generated, modes in the plasma. And it's a lot of data collection, a lot of very careful analysis. What we figured out is, yes, there are these benign modes as indicated in these spectrograms here. So this is a FFT over time, where you see a clear onset whenever you observe a clamping. So it basically means the pedestal builds up, and then you hit the critical gradient for instability to onset. You see the signature of that instability in the spectrogram, and then all of a sudden your gradient stays clamped, and we identified different sources, and I've wrote even review papers on like how these edge instabilities behave in fusion plasmas. One nice feature is we can now we have our hypothesis on how the pedestal and these instabilities work. Let's probe them. So I've been working with a graduate student to modify the edge current density by a perturbation. And the way we did that is by jogging up and down the plasma. And you see the z-axis coordinate, this is in meters. So this plasma is this much taller than I am. And within 5 milliseconds, you're gonna ramp it by this much up and down. That leads to a depletion of your edge current. So the current profile is going to flatten out. That means the magnetic field that is created through that current is going to change, and the instability, which is bound to a certain helical pitch of the field line, is going to shift radially. And that will indicate itself by a chirping, so a change in frequency of that mode. And what we did is like we studied the instabilities that typically set on and chirp up in frequency. And once we kind of made this radial oscillation, modified the current profile, all of a sudden they start coming down in frequency. And so this is an indication that we were able to modify and like kind of experimentally test these micro-carrying modes or MTM hypothesis in our reactor. And we can even make predictions of the most unstable mode numbers, which are the toroidal harmonics of that instability. And that was really nice. And here are the predictions and the experimental measurements are sitting below. So I think that was a really, really neat piece of work of a graduate student. Now coming, okay, we understand which physics limits the pedestal. How can we predict which kind of pedestal structure we are getting? And there I have been working on basically a database study. So this was with a Suli research intern, actually at PhD. And we compiled like over, I think, 10 years of operation, 30,000 shots, and made a neural network prediction of the pedestal height and width. And if you know the height and width, you kind of get an estimate of what the gradient is. And so that database is now used to validate pedestal models, particularly the so-called EPED model. And this has been, like this project has passing on undergraduate students for now, I think, the 5th generation. So now we're using our, not first principle, but the gold standard for this edge pedestal prediction models, which is so-called EPED model, and compare that model to our experimentally measured height. And we say, what we figured out is that in many cases, we have actually a limitation of that pedestal below that limit. So there are other types of instabilities that lead to the limit. Sorry, I'm probably moving too much. Out there. So there are many other instabilities that might lead to a reduced pedestal height. And again, the pedestal height, so the pedestal pressure, that is what goes actually squared into your fusion power in a reactor. So it's really important to understand the mechanisms that set this up. And even more important is like, can we do something about it? And so we not invented, but we added an actuator in our control system to start controlling the pedestal. And we're doing this by using so-called magnetic perturbation coils, MP coils. And these coils are coils that create radial magnetic fields. So on purpose, you destroy the axis symmetry and enforce a toroidal periodicity of your magnetic field structure. So rather than having a cross-section, you now have like a wonky torus. I mean, the deformation on the surface, again, plasma is this high like me, the deformation on the surface is like this much. But this already creates a so-called density pump out. So you have magnetic flux lines that are connected from this pedestal top towards the wall, and which particles can escape. And so this is a way how you can control the electron density at the pedestal top. And the goal here is to increase this separatrix density, so the density at the outermost edge where the confined plasma starts to interact with the material, you need to increase this density to protect the wall. The higher the density, the lower the temperature at constant pressure. So in order to decrease the temperature, you need to increase the density there. And so we threw that in a feedback control algorithm, sketched out here. And the nice thing is now if you plot the pedestal top density and the separator density, typically you would add gas and you would want to push up the pedestal top density, it goes up. And so your separator density does, but with the control, you kind of maintain the pedestal top density and increase the separator density, which is very favorable to protect the wall. This has been even taken on by another generation of students that I'm not advising anymore. You can perform Elm control and Elm feedback control. So you avoid these instabilities at all by controlling the pedestal to be below this instability onset threshold. So the engineering solution to this whole pedestal edge localized mode instability is get a control system and the appropriate actuators to counteract the edge stability. Breakpoint. Questions? No?
I arrived late, but I maybe missed it.
Yeah, sorry.
Can you talk about how you're making these measurements, like which tokamak and
Yeah.
what equipment? And if you already covered that, I'm sorry.
No worries.
You can
I'm
talk
working
about-
with the D3 tokamak. I worked on the NSTXU tokamak, which is currently down for maintenance. I worked on Aztecs upgrade and I'm working on K-Star. So I'm working on tokamaks around the world. But these measurements and this stuff was mainly done on Aztecs upgrade and D3. So the edge pedestal studies has focused on D3 and Aztecs upgrade because they have the highest resolution diagnostics. The point is you're trying to measure whatever, 5 kilo electron volts at a radial resolution, like that gradient is not that larger than this, and you can only do non-perturbative, you cannot use Laggner probes or anything. So the challenge here is really to have high resolution diagnostics from pretty far away. So we do this with Thomson scattering, for example, or the lithium beam would be another measurement to do I can provide you more details on that.
Okay, and just one follow-up.
Right.
So then, can any of these measurements be done in a smaller laboratory, or does it all require these equipment?
These measurements can be done, they're developed in smaller scale laboratory, but obviously the data is most useful if you're getting it under under right conditions. So the good thing here is just a 2-hour flight to San Diego. The bad thing here, or everybody that works at user facility knows if you want to get experimental time in such a big user facility, it's basically half a year to a year of preparation work. And then it's like day 0 and your heartbeat is up there and you just try to get the data in, take the hits as they come and make lemonade. That's what we're pretty good at. Yeah.
For the edge localized mode,
Yes.
from your test and from your drawing, it only occurs at the lower half of the cross section, and there is a heat flow from the midpoint to the lower half.
Oh, yeah.
Why is that?
Oh, yeah, sorry, that is just illustrated. So plasma likes to follow magnetic field, right? Transport perpendicular to field lines because the gyro motion is very simple, transport parallel to that. So the flow of energy is indicated downwards in the cross section, but what really happens is you have like parallel conduction that goes downward, and the main source of heat is typically the outward side because of these ballooning modes. So the curvature of the magnetic field lines, the topology is unfavorable for instabilities on this outward side, and so the heat flux typically comes out at the mid plane. I don't want to jump 5 slides back now, but in principle you get your major heat transport on the outward side, and then you have a field line that is not connected to itself anymore, but it's connected to the so-called diverger on the inward and outward side, and then you can go kind of both directions on top of the plasma to the inward side or outside of the plasma to the outward side.
Okay, that actually leads into what I was going to ask. How does like measuring these ELM modes change as you approach the diverter where those field lines are crossed?
That's actually a really good question. So the modes are measured by the magnetic signature. So you use simply pickup cost. That's actually the pretty standard diagnostic. They have just a coil measuring current filaments, like perturbation in the current. In the diverter region, these edge localized modes, since they also transfer current, actually lead to homoclinic tangles. So you get like whole structures where the integrity of your field lines, like this that you get a certain surface does not allow anymore because of this current perturbation. So you get flaring, and even in the video you could see that you get these striations, and these are exactly these tangles that you have a current perturbation disturbing your equilibrium that much. And the main point there is, this is a lot of detail, the X point is a null in magnetic field, right? So in order to create this crossing at the bottom of the plasma, you have basically zero magnetic field there. And so if you have zero and you put a small perturbation to zero, that creates a significant magnetic field anywhere you're gonna go there. And so in this low field area that has a so-called high flux expansion, perturbations actually even like amplify more than where the magnetic fields are higher and other currents dominates. Good. Let's move on to the boundary. So we talked about edge localized modes and how flux hits the wall. Let's talk about the I would say integral part of the fusion reactor wall. And I like this analogy a lot because, well, fusion is the energy of our stars, but as we know from astrophysics, stars have a finite lifetime. So you can only burn fuel for so long until you have burned up all your fuel. And then eventually you get into a red giant, and I'm not an astrophysicist, but over the course of a billion years, your star is going to die. In fusion, you can have the same effect. If you use, for example, deuterium-tritium fusion, you start fusing it, great, you create helium. If the helium sticks around in that plasma, you get a so-called helium accumulation. So eventually, your fusion plasma is going to be made up of helium. Helium is way harder to fuse, and the fusion power will obviously drastically drop. And in the fusion reactor, the time scale of burn up of your whole fuel that would stay in it is about 100 to 200 seconds. So what you need is neutral convection. Luckily, transport works in the favor. So it's not a problem that the plasma confinement is too good these days. So there's a lot of plasma come out. But you need to find a way to separate the helium out and to re-inject the fuel that comes out. And this is all about creating convection. It's, again, a very nice picture of a candle on Earth where you have gravity helping you to create convection and actually bringing air to your candle, because if you cannot create that convection of the neutral gas around that candle, you are diffusion limited and your flame is not going to light up. And the same issue happens in a fusion reactor in this diverter region, where it's really about making sure that the plasma comes out, hits the wall, doesn't melt the wall, recycles as neutral gas, but then this neutral gas needs to be pumped away. And this diverter physics aspect, or so-called core edge integration challenge, where you want to maintain good so-called plasma exhaust, but a good performing fusion core is an integral part on the path to fusion energy. And I think that graph shows this best. So on the x-axis, you have duration of your fusion plasma. On the y-axis, you have the fusion triple product. Okay, so this is how long you can maintain plasma performance over time. So first of all, if you would, IFE systems would be all the way to the left here. They achieved ignition. The problem is it's not straightforward to scale this. Like, you need to scale it by orders of magnitude in sustainment in time. So this is where we're working on IFE. For tokamaks and stellarators, which are shown on this graph, the plasma transport timescales and the resistive timescales, so the timescale by which a current relaxes inside the plasma, are very well figured out, I would say, and we have achieved very long or operations of tens of seconds at high performance. But as you try to extend the plasma pulse, all of a sudden plasma material interactions, neutral atoms coming back from the wall conditions like neutral trapping, detrapping, starts to affect your edge plasma, and unfortunately like impurities or just the neutral gas gets transported back into the plasma and decrease the fusion performance. And this is the 2 points here, which is neutrals and material migrations are the main challenges towards an FPP, fusion pilot plant, where you want to operate basically at the high fusion gain and at a very, very long pulse duration. And so this is the research that needs to be done in order to make sure to maintain actually fusion reactions in the confinement system. So what we have done is build the LAMA, which is the Lyman alpha measurement apparatus. It's an absolutely calibrated hydrogen Lyman alpha diagnostic implemented on DVD. It's a pinhole camera system with a Bragg mirror that has like, I think, a 60 multi-coded layer to cut out the hydrogen Lyman alpha line at 121 nanometers. Interference filter that helps to support eliminating the parasitic lines that sit around that. And then basically an AXUV photo detector to detect the signal. And then we have to bring this out of vacuum and build a high gain, like 10 to the 9 volts per amps gain transimpedance amplifier system, which you operate next to a coil that runs several kiloamps of current. So you have 12 orders of magnitude of the signal you want to measure to the signal you get from the magnetic field coil sitting around. We learned a lot. Low pass filtering, noise characterization is very important. But using this signal from the hydrogen neutrals, you can infer the neutral density. So we can start to study basically the neutral plasma interaction, the edge boundary, which we haven't done so far. So this is LAMA in all its beauty as it went on. So here's basically a quarter, just to show a size. It's pretty compact. There's a lot of like fun engineering. This was a grad student at MIT. We discovered 3D printing of Inconel. So this base plate is 3D printed, has cooling channels in it. It needs to sustain, I think, 350 centigrade bakes. We have like special mirror mounts that we have to make all of this obviously vacuum compatible. Very nice exercise of putting like cerama bonds on the pins of the AXUV detector. That was a fun exercise. So all in all, there is a lot of like handwork that gets put into these things before you can make these measurements that are then shown at the Fusion Energy Conference, for example, last year, where we actually figured out that depending on the helicity of your magnetic field, so this is pretty complex in the writing of it, but in principle, we change the direction of the magnetic field either going around the torus or in the opposite way. And this, by keeping the plasma current in the same way, you're pitching the field upwards or downwards. So you direct basically plasma flows either to the inside, to the outside, or to the inside. And we show a vast change of the neutral density or the ionization source at the edge of the plasma, depending on how we run this configuration. That is very important because you see these asymmetries. That means that your particle source actually changes depending where your plasma configuration sits. And this particle source is what basically impacts the fusion performance. So, okay, what can we do about this? About neutrals recycling, not coming back, about impurities being released. So there is a tool that has been developed at Princeton Plasma Physics Laboratory, which is the impurity powder dropper. And we use basically boron to trap hydrogen neutrals. And this is called real-time Volt conditioning. This is an image of Aztec's upgrade, where you see the fusion plasma. So first, very good to know if you see these pictures, the really hot plasma is invisible because that radiates just synchrotron radiation. You don't have any kind of bound electrons that you can see. What you see is the cold plasma where you have neutrals. So you get these pinkish, the light of the universe, the hydrogen alpha line rings around the torus. And then basically back here, there's another diagnostic obscuring the view. We inject boron, and you actually see, first of all, it really nicely marks the pitch of your magnetic field line because the boron gets ionized and distributed along this magnetic field line. And then you see the blue light, which is boron 2 line that ablates. And what we want to study with this is, like, where does this boron go and what does it do to the plasma-facing components? So we set up an experiment on Aztec's upgrade where we had the impurity powder dropper injecting powder here from the top. And then we prepared a sample at the bottom here, at the diverter, at the outer diverter, which had inserts of tungsten, one polished, one unpolished, and we basically had the plasma striking on this. You know, with different RC values in order to manage the see effects of the surface roughness basically on the powder sticking. Also, what we did is injected enriched boron 11 so that we can distinguish intrinsic boron, which is regularly used for wall conditioning like low discharge boronization, from the actual injected boron. And after, I think, 5 plasma discharges, we see, well, this tile changed a bit. So you see layers of deposition. Oh, sorry, I'm pointing at the wrong, pointing here mouse. Okay. You see layers of deposition. Nope. I will just describe what's on the image. You see layers of deposition beyond this yellow dashed line, which is the location where the plasma interacts with the wall. Then you have a zone where you have some deposits like appearing on the edges of the tile. So this is where you have basically an edge that kind of screens certain areas of the material from plasma wall interaction. And then far out, like all the way to the top of the tile, you also see some deposits. Performing nuclear reaction analysis actually gives a really nicer picture. So you see a clear buildup of boron in the so-called private flux region. That is the region where you have plasma, but you don't see heat flux. So this is a region of very, very cold plasma, where basically, again, if you follow the arrows, the arrow goes around the plasma and hits basically all to the top of this yellow dashed line. This is where heat hits. Below this yellow dashed line, you don't get any heat. And this was actually not expected because we thought the boron is just going with the flow of the plasma and it's going to mainly strike above the yellow line. But what you actually get is cross-field transport. So there are drifts in the plasma that shuffle boron below the yellow line and deposit it there. And so you don't have heat flux there, but you get boron ingression. You build a very thick boron layer there, shown here by the private flux region. Then where your location of the plasma is, you clearly drop, because that is a region where you get a lot of heat fluxes and basically sputtering, so erosion of material. There's no net deposition then. And then basically the boron, which is the blue curve, builds up into towards the top of the tile, where you have less and less heat going on. Yes.
What is nuclear reaction analysis?
Which reaction chain?
Yeah, well, what is that?
So they use a tandem accelerator, and I think it's a deuterium beam that reacts with either the deuterium in the deposits, and you can basically then measure I think the fusion product. So you basically just launch a beam on it. I'm not a material scientist. I like to work with them because they know all these fancy techniques we're going to have a lot of other colorful images. I'm trying to give an interpretation what the plasma is doing here, but it is a very powerful tool to basically measure the boron deposition, which is the blue curve, and then the retention of the deuterium in these layers, which is a very big question, right? Because you have a deuterium tritium mixture, you're going to trap radioactive material in these layers, which is bad because you're building up inventory and they cannot easily release that. So we also see some deuterium injection. Then as a marker, basically we use intrinsic carbon, which is the bulk material of a tile. So these are tungsten coated tiles. Then you have like carbon below it. And so you have always some edges where there is no tungsten on it. So you have intrinsic carbon. And so the carbon basically validates the boron data here. Even going one day further, we can do some tip cuts through these deposits. So first of all, you see a staggering of these layers as we run plasma discharges. So each of these layer cakes is another shot of plasma. And then you perform EDX and basically measure boron that was deposited there, so the yellow signal, oxygen, which likely get into these layers when we had to remove it from the vacuum system. But there's also some oxygen trapping. You see the bulk tungsten below it. We even see like a tungsten grain that basically flaked off of the tile and then was kind of implanted on that surface. And you see the wall conditioning effect, which is this moly nickel iron stuff that is intrinsically around in the machine, but then gets buried under these layers. So boron is a low C material. There's little branch down in the plasma, great for plasma performance. This moly iron nickel, high Z, does a lot of branch down. So if you bury this under a layer of boron, that typically improves plasma performance by minimizing radiative losses. Okay, so we've learned a bit about the physics. What can we do to engineer our wall solution? So what we are going to do is in K-star this time, because K-star is a superconducting long pulse tokamak, you can run 20-30 second plasmas that have the right duration to study neutral and wall conditioning effects. We have this tool, this is the impurity powder dropper. It's basically a powder shaker. If you have sugar powder, you just shake this, but it's really tough in vacuum to feed powders that are like hundreds of micron size, because if you have like any kind of moving parts, you get it stuck, and then the feeder is not, and you want to have a linear actuator. So the idea was to come up with piezo shakers, and depending on the amplitude of these piezo shakers, you can control the injection rate. And now we hook this up to the plasma control system and sensors that basically enable us to qualify, oh, this wall is gonna be bad. So then the plasma control system jumps in and says like, shake a little, drop a little bit of boron, get the wall conditions back to fusion relevant, and extend the high performance plasma pulse by that. The other thing is so-called detachment control. So you inject boron nitride, which basically gives some nitrogen to it, which is an impurity that radiates very well at plasma temperatures of 10 eV because it's several electrons. So you can create a radiation front in this diverter area, so very, very localized. And by maintaining that, you kind of can dissipate heat before it actually hits the wall. Questions to that? I will go a little bit longer, I hope so.
No,
Okay.
yeah, we have 15 minutes back in. It's fine.
Okay. No.
I had a question.
Yeah, sure.
Why is the boron dropped on the top and not the inboard plate? Boron only has to be outside.
Technical question, because we don't have ports there. So there are machines where you can put it to the inside. Practically speaking, the transport to the inside, because you're at the top of the plasma, is fairly easy because you have a magnetic connection length that goes down. So it's actually very well transported to the inside. It is originally just port availability. We're going to now ITER, who decided to go full tungsten at first, is interested in putting on this technology because they're so afraid of the tungsten influx might ruin their fusion performance. So there is an ad hoc working group in the international tokamak community where I'm part of, where we just try to try together which demonstration experiments we need to do to make this tool available. So this tool, or powder dropper, available on a nuclear facility. It's just not straightforward, but
something just occurred to me here in this. So if this were a burning plasma
yes.
with a big neutron flux
yes.
coming out, you're going to, in real time, as you drop this boron in, you're going to be creating, on the good side, tritium. It's going to be energetic tritium, energetic deuterium probably also from DN, and of course alphas as well. Could this be a positive or a negative? Could it be a boost? Yeah, boost, basically.
I have not, so thanks for bringing it up. I have not thought about this. I think, it's a significant amount of boron. I have not calculated like the neutron flux density that you will actually need, because these are like tiny flakes, right? You're talking about milligrams per second injection. It compares to the tritium fuel that's in the plasma. It's still a lot, but a lot of the stuff just like melts into droplets, hits the wall. So not everything gets like fully ionized, and I would need to look into the residual time, like how long this boron stays in the plasma and what's the chance of like being hit by a neutron.
So the good news, just to be clear, the good news is I don't care what shape this is in. It could be a centimeter thick.
Right, yeah, as long as
the neutrons will break it up, and the triton will be born with a lot of energy.
Right.
So it will emerge into the system, or it'll go in all directions.
Right. I'm just more like if you fuse it basically in the boron droplet, if you create it in a droplet of boron, the tritium, it's not available for another fusion reaction, right? It's just going to be staying trapped.
But you could have a piece of this. It'd be worth calculating this.
Yes.
And a warning note here. The cross sections in NDEF that are used for the secondary particle production for neutrons on boron are wrong. Just do keep that in. They are actually wrong. They're identical for boron 10 and boron 11, and they're not.
No.
Okay, so just I think it'd be an interesting idea if you have the ability to sprinkle in here. This could either be a bad thing or a good thing. It could be a very good thing, boost.
Yeah, exactly. I mean, it's definitely worth to look at it. It is a challenging research because of this like co-deposition. Like people are really afraid of like building up layers of like millimeter thickness that then delaminate and come off. But I think with boron, you could actually still tolerate a big chunk. If that same size chunk you have it in tungsten, your fusion stops instantaneously with a big bang. Okay, my final part was about heating and current drive systems. So in order to study plasmas that are very hot, you need heating. And there are several ways to heat magnetically confined plasmas. One of that is by wave heating. So you try to hit the resonance frequency of the gyro motion of the electrons or the ions, which is called electron cyclotron heating or ion cyclotron heating. Plasma has a lot of waves. You can do lower hybrid injection as well. But the most commonly used heating source in test and fusion experiments are neutral beams. And so this is what I started a year and a little bit ago, is working with the neutral beam injection team at D3D. So the nice thing is, it's also plasma physics. You need to have an ion source with an arc discharge. You accelerate ions. You shoot them through a gas target to neutralize them, separate out the residual ions, and then inject a neutral beam into the tokamak. Why you need to inject a neutral beam? Because an ion beam would be just bend it away and hit your wall. So not good. So that is the reason why there is a neutralizer in here. And in order to create heating power, this plasma needs to create a lot of ions. So just having that said, this is one of the 4 neutral beam injectors on D3D. This thing is about 20 feet long. This box here at the back where the ion source sits is about 1.5 my height. And this injects about, like the 4 boxes together, inject about 16 megawatts of heating power. So if you want to inject 16 megawatts of heating power at an acceleration voltage of 80 kilovolts and a neutralization efficiency of 50%, you currently draw 60 amps out of each of the 8 ion sources. And these have been working very well, but developed in the late 1980s. So these are so-called arc chambers with filament discharges, so tungsten filaments with an arc going, a 3000 amp arc going in between, and it's about 100 kilowatt arc discharge that creates these ions, and you get like 1 kiloamp of ion current density per square meter out of this source. But you have many connectors, and you have many points for failures because these filaments are eroded and that material gets deposited on insulators, and then you can have what's shown on the left, arcs basically ruining your source. And just to give you a sense of scale, so the slit or extraction slit of this ion source is about this high. So this is the picture all the way to the right. And the plate that you're looking at that is burned is about like this wide with a nice cutout. So there's like massive failures. And the problem is, if you wanna, what D3D wants to do now is like push up to 20 megawatts of heating power. So how do you do that? The neutralization efficiency is limited by the ion energy that you shoot into that target. So this is a charge exchange process that becomes unreliable. So you cannot increase the voltage for the acceleration. So you need to increase the current of the ions. If you want to increase the ion currents, you need to dump more power into the plasma discharge, which means you need to increase the arc current. And that causes further damage. So the solution here is to build new ion sources, engineering solution, where you use radio frequency inductively coupled plasma. So you build an antenna around that chamber, you don't run a current through the chamber, you couple radio waves into the chamber, about 150 kilowatts, and then basically draw now 85 amps of positive ion current out of that source. And DOE has been very grateful to fund this project with about $2 million. So what I'm going to do at NC State is build a test setup, so-called loop-in, which is on the next slide, to optimize RF coupling and plasma uniformity, because you need to have its gigantic grid and you want to have a homogeneous ion density to draw a very homogeneous ion beam. And obviously you want to simulate that, and so we have good modeling capabilities of the so-called HPM model, hybrid fluid kinetic simulation. So we are going to validate that at loop-in. And my grad students just started to basically procure the parts of the chamber, but again, engineering. you have a quartz dielectric vessel. How thick you're going to make this to sustain the pressure of the atmosphere, to sustain the heat that is coming out, and with minimal thickness. So we're doing finite element simulations. We're trying to match the neutral flux that is going behind the plasma. And so there are a lot of like ongoing challenges. And once we have qualified our antenna and our plasma delivery system, so Lupin is going to have in the same power density as the full scale prototype. We're going to scale this up by a factor of 4 and build basically a prototype for a full neutral beam injector. So with this, I would like to summarize. I've talked about pedestal feedback control with nice colorful points and inter-modes, which I think have contributed a lot in the field of plasma physics to this. And I think the engineering solutions there is really using the actuators and means of control to avoid these instabilities at all. I've talked about wall conditioning and neutral gas reduction, and basically enabling access to high performance plasma regimes. So Lupin basically supports this power increase. With a higher beam power, you can simulate basically higher plasma pressures, and there are regimes like the Super H mode that affect the would boost the confinement of the plasma as well. I have one final slide, which is, I think, my perspective. I presented a lot about plasma physics because I think this is a really, really interesting topic. But if you want to deliver fusion power, you need to start engineering the systems around that plasma. I think from a TRL perspective, there are many, many things that can be optimized and resolved on the plasma end. So, sorry, green is high technology, right? And so I think the plasma is actually pretty advanced. What we don't have is the heating and current drive techniques. We have no idea about the materials that are going to be in a fusion reactor, and we have no ideas about how the fuel cycle in the fuel, or we have ideas about the fuel cycle. We have no engineering solutions to actually bring these ideas into a fusion power plant. And so I think my approach here is from the knowledge of the plasma physics. So you always need to engineer a solution that is compatible with your plasma inside and compatible with the conditions that the plasma provides. But I'm moving more and more to the direction where I think we need the innovative engineering to deliver the solution to actually get to a fusion power plant. And with this, I want to thank you for your attention and open it up for another round of questions.
So I have a question about, I think you said you were using data collected at the D3D as inputs to a neural network.
Yes.
To characterize is it the height of the
Pedestal, yes, correct.
Okay, so I guess my question is, what was the architecture that you used for the model, and why did you choose that?
If you're not an AI expert as myself, you let the model choose itself. No, there has been a Lawrence Livermore lab, Katie Hummingbird has been developing the so-called GINN framework, GINN, and that is basically a framework that runs like different neural network architectures and kind of scopes the residual errors. So that has been actually a really useful platform.
Is that open source?
It is open source, yes. So actually an undergraduate student at the Zulu Institute, she's now PhD student in Stanford, all on ML. She did the legwork on like collecting, she wanted to do ML. So she was like, oh, we need this activation function. Like, I'm learning here, like, thanks for teaching me all of that stuff. I don't know, but the GINN is open source. It's a GitHub repo. And you can, like, I think Kelly has been using it for like shot design on NIF. So like neural net fast predictions for the neural net. And as far as I know, my grad student just downloaded it. Undergrad student at the time just downloaded it from a GitHub repo. So I think it was a really powerful tool and got better prediction than like linear regression and like the standard basis.
So the Stone and Livermore, they were actually was programmed to study driving heating the tokamak with a FEL, which is now a very mature technology, just putting in microwaves just above the plasma frequency.
Yeah.
Why are neutral beams you think the tool of choice rather than microheating just above the plasma frequency?
neutral beams are to be debated. Let's say like this, they require, so for penetration, you require high injection energy. You need to go to negative ion. Your beam becomes as long as there's room. You need to build facilities like in Padua, you have a 1 megavolt accelerator, which even the power supply doesn't fit this building. So this is ridiculously crazy. The flexibility of the neutral beam is this big trump if you go to use a facility like D3D. For the wave heating, as I say, you need to hit resonance frequency. So if you change the magnetic field by a little bit, this resonance is going to move. That means you can trash all your equipment on the back end, because the power supplies will match up on all the like production. So for experimental studies where you typically do like variations of the current in the plasma, the magnetic field is super versatile because it doesn't care about all these things. It delivers power to the plasma. And so for experimental facilities, the neutral beams are gonna be the state of the art anyways. For the reactor, I think we need to figure that out. But since I've operated enough tokamaks in my life to see which heating systems are the most reliable ones, these are neutral beams. For whatever reason, that is the only technology where you don't have like vacuum leaks. These megawatt class gyrotrons, they fail, and it's a really tough engineering problem. Actually there is somebody out in the Bay Area like discussing about like gyrotron improvements as well. So they're just not reliable and not like long pulse capable at this stage. And so there's a lot of engineering actually going into making this better. But like as I said like earlier in the meeting, a neutral beam comes at like $100,000s. Gyrotrons are in the $1 million class, and unfortunately they don't work. So we will see. Thank you. Good question. Do you like the food? Well, feedback now because there might be another talk someday, so you should order it.
First of all, I love this figure. I like the color coding thing, or the whole idea of trying to point to where the different TRL levels are present. But I want to ask you, there's a couple of things. You got the green, you got the orange, you got the red, then you have the black, which I assume means you think there's it's established. It's the highest TRL, or is it nothing? You haven't ranked it yet.
I had that not colored, and I think I missed these two. I think the magnet coils I was not sure, right? So I would say it has the highest TRL for conventional superconductors. Either is going to be built out of that. Spark is pushing HTS, so it depends on which technology for magnets you're looking at. So I was just not picky. I would say there is a high TRL level magnet technology available, and then what CFS did is push the TRL and super HTS coils up. And for the generator and turbine, I think there's just no innovation in fusion going into advancing this.
I agree. So my question, magnet coils, I agree. There's these proven technologies. What about when you put neutrons around them?
Well,
would you deign to color it a particular color in this?
Well, first of all, I think you need the neutrons in your blanket anyway. So like for cooling reasons, you cannot tolerate any thermal fluxes into your, like any significant thermal flux in your coil. I was working on a trigger reactor in Vienna in a superconductor in that, where they did neutron irradiation of HTS tapes. So I know where you're going. It doesn't look good. So then you talk to MIT experts, and they're like, if you irradiate it under operation and it's cryogenic, then it's not too bad, and we'll eventually figure. I'm apparently like they did critical field measurements on the alignment, and you're off 1 degree, and the critical field on that tape is gonna kind of be like half of it, or so. I mean, I'm aware of all the engineering challenges. I am glad that CFS took it on, and we will see how far they get. In the end, I think practically you have to put enough neutron shielding in between these coils and the blanket and the fusion plasma anyways, because of like cooling requirements. That like you have liquefiers running all the way in the back end to just like cool off these couple of kilowatts, and yeah, liquid helium is not that good of a coolant that it can cool off like kilowatts of heat being deposited in that coil. So I agree with the sentiments, and I think I joked with Carl earlier. in one meeting where we said like, yeah, it might that spark kind of burns like its coils within like their first pulse. I think they will sell it as a success if they produce so many neutrons that they burn their coils.
That's very good.
That is a way to work it, and so this is all this kind of framing on the neutron question. But I'm aware that it's a challenge, and we'll see. I think they're fairly confident that it's figure. I think they're more worried about quenching these days.
Yeah.
So,
Other questions? I know it looks like we've gone over, but there's actually some time built in to the schedule. So, any other questions, folks? If not, a number of you get free lunch, proving that, disproving that there's no such thing as a free lunch. Okay, there is. Okay, that's going to be happening afterwards. But let's thank Professor Laggner again for an excellent. We will slowly migrate over to back to Echeverry Hall. We were here for this meeting. But we're going to really take our time because your next meeting is with Bethany Goldblum.